channel on now, and I'm going to start to record also. Okay. Okay. Very good. So, welcome to our one-word probability seminar. So today we will have only one courageous speaker that's going to give us two talks about two-scale convergence and applications. So it's really a pleasure to introduce Alessandra Faggionato from la Universidad La Sapienza in Rome, who's going to talk. So she's going to give a first one-hour lecture with a gentle introduction to scale convergence for random walks in random environment.
Okay, thanks. So I thank the organizers for the invitation. And okay, we'll try to be pedagogical in this first talk and hopefully provide a gentle introduction to scale convergence for random walks in random environment. And in the next seminar, I will discuss several applications to homogenization, hydrodynamics, and random resistor networks. Okay, I start saying that two-scale convergence has been developed for homogenization of differential operators non-random by Wetzeng, and then further developed by Allaire. And then it was, so the theory has been further developed by, so for random differential operators, in particular by Zhikov. And I also point out I point out this paper of Zhikov and Piatnitsky, which has been very inspiring for my results. And also I point out this that there is some material in the book of Armstrong and co-author on quantitative stochastic homogenization. So I will deal with random walks in random environment. So I fix my setting. Okay, the story starts with a probability space, so this is not a surprise. I will call, so omega is the space, and omega is the set of environments. In what follows, I will deal with a continuous time random walk in the environment omega, and it will be denoted by xt omega, so t is continuous, is in continuous time. And this random walk has a countable state space denoted by omega hat, and it is a subset of RD, of the Euclidean space of Euclidean space RD. And so the other notation I will use is the following. I will write R, X, and Y, R, X, Y of omega, the jump probability rate for a jump from X to Y. Okay, so in order to state the assumptions and to complete the general setting, let us start with an example. So I consider, so a guiding example, the random walk on the supercritical percolation cluster. So let us consider ZD, so the lattice ZD, and I will denote by ED the set of unoriented edges of ZD. Okay, so I have my lattice, and to each edge, unoriented edge, I attach a number which is 0 or 1. So the collection of these numbers is the environment omega. And as a law for the environment, I can take, for example, the Bernoulli product probability on omega with the parameter p. So p is the probability that the number associated to a given edge is 1. Okay, and I suppose p to be larger than the critical probability for bond percolation. So due to this assumption, okay, I know, because of bond percolation, that there exists a unique infinite cluster in the graph given by bonds edges with associating number equal to 1. And I will denote this unique infinite cluster omega hat. So here you can see a picture of the so-called supercritical, so this infinite cluster in the bond percolation. And to define the jump probability rate, I write nx omega, given x in this cluster, for example, this point here, I will write nx omega for the number of adjacent sites to x in the infinite cluster. So nx omega is the degree of the site x in the supercritical cluster omega hat. And the simple random walk on the supercritical percolation cluster has the following jump probability rates. So the probability to jump from x to y is 0 if x and y are not adjacent in the cluster, and if they are adjacent, it is given by 1 over the degree of x. So if this is x, the particle jumps to these two nearest neighbor points with the probability rate 1/2. Okay. So let us see the property of this simple random walk on the supercritical percolation cluster. So a first property is that it is irreducible. You can, starting from one point, you can visit any other point. Moreover, it is reversible in the sense that it has a reversible measure, not a reversible probability measure, but a reversible measure, mu omega. And in my case, okay, I use this notation also because it will be the notation also in the following. So mu omega is simply the measure with the support the infinite cluster, so the state space of my random walk, and it is given by Dirac measures, and the weight associated to the point x is given by the degree of x, the site x in the infinite cluster. So here I have reported the detailed balance equation given reversibility. But then there are also other structures indeed behind this random walk. So the law of the environment is indeed stationary for the action of the group ZD. So the group ZD acts on the space of environments in the following way. So given G in ZD, you can define a map from the space of environments to itself. Simply define as follow. You translate the environment back, physically, you translate the environment back of G, okay? All the environments, all the numbers 0, 1 associated to edges. But the group ZD indeed acts also on the physical space RT. So we have two actions, and the action is the trivial one, the one given by translations. And then, okay, I have also some covariant relations. So the jump rates and also the reversible measure are intrinsic. So they do not depend on how the coordinate axes are fixed. So we have, for example, the probability rate to jump from x to y in the translated environment, tau g of omega, is equal to the probability rate to jump from x plus g, to y plus g in the original environment omega, and so on. Okay, this is an example that lives in ZD, so the infinite cluster lives in ZD, and the group acting on the probability space and on the Euclidean space RT is ZD itself, but you can consider something more amorphous. For example, let us consider the random walk on a simple point process. So now the environment, the space of environment is given by the family of locally finite subset of RT. So an environment is simply a family of points in RT, okay, locally finite. So omega is this collection of points, and the state space omega hat of my random walk equals, in this case, omega. And you can take several examples of jump probability rates. So for example, you can say that the rate to jump from X to Y decays exponentially in the distance between the 2 points. So this random walk has the same property as the same structures outlined before. Okay, you have, I just comment something that is, here the counting measure is the reversible measure, okay? And now, and this is the difference, the group that acts both on the environments, the set of environments, and on RD is given by RD itself, okay? So, for example, if the environment is given by this family of points xi, the G translated environment omega with a G in RD is given by the family of points xi minus G. Okay, and then I can, here I didn't choose a particular probability P, I take a P which is stationary for the action of RD on omega. Okay, so we can, I formalize. So we have seen two examples, and now this is the general setting of my discussion. So for the random walk. So I have the following objects. First of all, I have the probability space where omega is thought as the space of environments. Then I have a group, the abelian group, which can be ZD or RD. The group G acts on the space of environments. Okay, so I have this action. So for each G, I have a map. For each element of the group, I have a map from omega to omega, and it is an homomorphism. Okay, and I have also that the group G acts on RD by translation. So the classical, the standard translation of points in Euclidean space. And then I have, if you think to my example, also other characters appear. So we have a measure on RD, which is a pure point measure. So this was mu omega, okay, which is a measure with the supports given by point, okay. In this picture, the points are the red points. And each point has its own weight. So this is the weight. And then you have times the Dirac measure in X. Okay, take this weight positive. So the support, omega hat is really the support of the measure mu omega. So omega hat is related to the random walk because it is the state space of the random walk. Xt omega has a state space omega hat. And then the other object I have are the probability rates that specify the dynamics. So R, X, Y of omega is the probability rate of a jump from X to Y. Okay, so this is a very general. And then I have the assumptions exactly as in my example. So I had that, I assume that the law P on this of my space of environment omega is stationary and ergodic for the action of the group G. Okay. Then I assume that the random walk is irreducible on its state space, so it can visit all points of the state space. So the measure mu omega is related to the random walk in the sense that it is a reversible measure for the random walk. And in order to avoid pathologies, I assume also that it has expected, it gives mass, finite mass to finite sets, also in average with respect to omega. And then I have the covariance relations connecting the jump rates with the actions of the group G, and also for the reversible measure. Okay, so I hope that this is clear. Okay, I have to say that one can indeed, in my, so indeed I have considered even more general settings so for example, if you consider the random walk on the hexagonal lattice, which is given, okay, a random walk on the points of the hexagonal lattice, then in this case, the action of the group CD is on R2, so look at this action. The natural action, the natural translations of R2, where the hexagonal lattice lives, is not that G acts by translating any element of G. So, if your element G of Z2 is G1, G2, these are the two coordinates, then you translate by multiple of the fundamental basis of this lattice. Okay, I don't enter in the detail. In order to simplify the notation here, I will restrict to the previous assumptions, but when dealing with lattices, you can also extend the assumptions. And so as a consequence, this setting is very general. You have plenty of examples of random walks in random environment with this structure. For example, the random conductance model on CD or on a lattice, the random conductance model on CD with long conductances, okay? The multivariable range hopping, I will discuss it later. And also, for example, the random walk on the Delaunay triangulation. These are all examples, but there are many others. And they enter inside this formalism. So I don't see the chat, so if there is some question, please let me know. So here, this was the basic notation for the random walk. As I told you before, in order to simplify the notation, as in the first two examples, I will take the trivial action of the group G on RD, that is to the element small g. If G is in my group, which is CD or RD, you translate by G, okay? And to simplify the notation, as in the example of the random walk on the supercritical percolation cluster, if G is CD, I suppose that the random walk lives in a subset of CD. That is, its support is a subset of CD. Okay. Now, in order to understand, to use in optimal way the ergodicity of the environment, a very important efficient tool is given by the Pan distribution. So it is provided inside the theory of random measures. Here I have indicated some references, okay, for convenience, okay, if somebody is interested. But anyway, I will start from zero. I will define the Pan distribution associated to the reversible measure. So recall, omega FP is the probability space of the environments. Given the environment omega, we have the reversible measure for the reversible measure mu omega for the random walk. Okay, I suppose that I add this assumption, which is very natural, that mu omega has a finite positive intensity m. It means that if I take, for example, a box 0, 1, 2D, then the mass given by the reversible measure has a finite expectation with respect to the law of P. Okay. Then the Pan distribution that I denote by P0 is an object associated to the random measure mu omega, and it is a probability. It is a probability on the space of environments. Okay, so it's a probability on omega, and P0 has a particular support, which is given by omega 0. So omega 0 are the environments. So if you look at the last expression, the environments omega such that 0 belongs to the support of mu omega. So recall that omega hat is omega hat. Is there a question? I don't hear. Okay. Okay. So omega hat is the support of mu omega. Okay, so it is also the state space of my random walk. So there is a more elegant, deeper definition structure behind P0. Here I gave directly the result. So when the group G is RT, as in the example of the random walk on the simple point process, then P0 is obtained by the following spatial average of P. So P0 of an event A is equal to 1 over m, m is the intensity, and then you integrate, you take the average with respect to P on the environment omega, and here you integrate with respect to the reversible measure in this finite box, and then you consider the characteristic function A evaluated in the translated environment by X. Okay, I gave it for completeness, but okay, it's not essential for what follows to keep in mind this formula. In the case that G is equal to ZD, as for the random walk on the supercritical percolation cluster, the Palm distribution is a much simpler, at the end I reduce it to something much simpler. So in particular, the intensity, as you can see, as a mu omega is defined here, the intensity is simply the expected value of N0, the weight given to the origin by the reversible measure, and P0, the Palm probability, the Palm distribution probability of the event A is simply this ratio of expectations. So here in this notation, so I have extended the notation. When I write the expectation of N0, I mean that so N of X in the environment omega is the mass given by the reversible measure mu omega to the site X. So it is in particular, this function is 0 if X is not in the support of mu omega. Okay, but what is important of the Palm distribution is that it emerges. So it describes very well the ergodic properties of the medium. Okay, let us see. I give you a fact, restatement of the ergodicity, and then we will see in the example that at least for the random walk on the supercritical bond percolation cluster, we recover the standard Birkhoff theorem. So in what follows, I write delta L for the box in RD of radius L, okay? And then the assumption of ergodicity of P, I record you that P is ergodic, implies the following. So if you take a function f defining omega 0, which is the support of the Palm distribution given by the environment such that the origin is in the support of mu omega, and in this, which is also the state space of the random walk. So given f, which is measurable and non-negative, or if you want integrable with respect to the Palm distribution, then the limit when L goes to infinity of 1 divided the intensity m of mu omega, and also 2L to D, so the volume, the Legbeck volume of this box, times the integral on this box of my reversible measure, so with respect to the reversible measure of the function f, but evaluated in the translated environment, tau x of omega. So f is unobservable, but you are focusing f around x. Okay, this is the expectation of f with respect to the Palm distribution. So E0 is the expectation associated to the Palm distribution. So let us see in the example of the random walk on the bond percolation cluster. So I told you, I observed that the reversible measure mu omega is the following delta pure point measure. So it's a sum with x in the infinite cluster omega hat, and then you have a delta x times, so the weight, which is nx of omega, and it was simply the degree of x in the infinite cluster, okay? Note that nx of omega is also equal to the degree of the origin when you translate the environment. And recall you that I said that the Pan distribution P0 of an event A, since the group G is CD, is simply this ratio. And this is the expectation with respect to the original measure. So at the end, you can rewrite the left-hand side in this formula is exactly this. So 1 over m times the number of points, no, the volume of the box, and then the sum with x in the box, so intersected with CD of this function. N0 in tau x of omega, f in tau x of omega. And by Birkhoff-ergodic theorem, we recover, so we get this limit, which is exactly the expectation of f with respect to the Pan distribution, okay? So at least with the discrete structure, it's not new, this formula. But okay, we can also restate, it's useful to restate ergodicity at a two-scale level. Okay, here I have two pictures. So this is the dog of my parents. And so the idea is that up to now, what I have described is the microscopic world. It's something that I was observing with the microscope. So I had a microscopic picture, okay? But I'm interested at the end also to the macroscopic world, okay? So in order to in order to pass from one picture to the other, I have to zoom in, okay, if I want to go from one picture to the other. Okay, and so I have to introduce a scaling, okay, to distinguish these two pictures. So if there are some questions, I don't see the chat. Milton? Okay, I'm
taking control of the chat, so okay. It's okay. And
okay.
haven't been any questions.
Okay, thanks. Because not only I don't see the chat, but I don't see anybody. I wanted to be sure that I was speaking to people.
Yes, okay.
I was not disconnected. Okay, thanks. Thanks a lot. Nice to hear a voice. Okay, so in order to distinguish between the two pictures, microscopic, micro and macroscopic worlds, I introduce, I need a scaling parameter. So epsilon is a positive number, okay? So here it is a microscopic picture, as before. I have mu omega, this is a representation of my reversible measure mu omega. So it is a sum of delta measures, direct measures with some weights, okay? And then I wanted to zoom in, okay? I have to reduce the length. So I multiply all lengths of epsilon. So in this case, I divided the length by 2 because epsilon is 0.5. And I introduced the rescaled reversible measure mu epsilon of omega, which is the following. So it's the sum with the x in this, okay, x if you want in this point, but then I take the direct measure in epsilon x, so I'm summing on these points, and the weights are the previous weight, but times epsilon d. Okay, I have to reduce the weights of epsilon d. So this measure, because of ergodicity, okay, one can check that is a good approximation. So, so when epsilon, let us say, when epsilon goes to 0, this random measure converges to the Lebesgue measure times m. But we can be finer in investigating ergodicity. Indeed, we have the following result. So take a function f, which is the function of the environments, and non-negative, integrable with respect to the Palma distribution. Then there exists, you can find a subset of environments which depends on omega, which has full probability, and for each environment omega in this subset, you have this nice property. Whatever is your test function, spatial test function, so for each phi, which is continuous with complex support in RT, we have the following limit. So the limit when epsilon goes to 0 of the integral with respect to the Risqué reversible measure, mu epsilon omega of phi in X, time the observable of the environment, but you have to center your microscope around the point X and zoom out. Okay, so this limit is the integral on RD of the X, M, phi X, and then the expectation of F with respect to the Pan distribution. Okay, so we can add the difference between this limit and this limit is that now we have also considered this contribution. Okay, we are observing the environment. Okay, here you see two colors, red and green, because the red X means that the position X lives at the macroscopic scale, while here I have a zoom out, so X divided by epsilon lives here in the microscopic scale, okay? And so it is convenient to understand that, because now I will define the two-scale convergence. It is convenient to rewrite this expectation as an integral with respect to omega, but I have to distinguish because here it is a fixed omega, so here I have to change name or vice versa. And indeed, I have written in this way, so this will be useful. So the formula I gave you before is this one. So I say that for any omega tilde in this good set of subset of environments, which has probability 1, whatever is, so and this set depends on F, this function here, for each test function phi, continuous with compact support in RT, we have the following: the limit when epsilon goes to 0 of this integral with respect to the fixed environment omega tilde is this average. And here we have an average, a spatial average, so as an integral with respect to the x, but we have an average among all environments. So here we have, look, here we have only one environment in the left-hand side. And the effect of taking the limit of epsilon going to 0 make emerge an average over all environments omega. Okay, so this is the ergodic property. So,
Sandra?
Yes?
Could you comment a little bit on the equivalence or in the difference between this notion of ergodicity and the more familiar Birkhoff theorem?
No, okay, this is indeed it's just, you have just to work a little, but it's a consequence of Birkhoff theorem. So it's not a new form, it's not something new, something stronger. Indeed, it's a consequence of a Birkhoff theorem. Okay, that is, if you take out a phi, you get the Birkhoff theorem essentially. Usually, when we do, we apply Birkhoff theorem, we take the average. Imagine Birkhoff theorem on CD. You take the average on all points on CD, and you take F evaluated in the environment. Okay, here I am. See here X in this macroscopic space. But here, so if you want the Birkhoff theorem, is such that the phi of X is the characteristic function that X belongs to the unitary box. Okay. Okay, it's a special case. I hope it's clear. Is it clear? Okay. Yeah. Okay, so it's for a special phi, you have a Birkhoff theorem. So when you average on a finite box, but indeed you can take something tuning in X and take the test function phi. Okay, and now, sorry, let us see if I can. Okay, so I have written the two-scale, so the ergodicity in this two-scale form because two-scale convergence now is not something free. It's something that is a property that I want to isolate, and it is a sort of empowered two-scale ergodicity, two-scale averaging. So it's the following. So we have that, okay, recall that, okay, I assume that the 2P is separable in order to continue. So it has a countable dense subset, G. Okay, now fix the environment omega tilde. Omega tilde is fixed. And take a function which is in the L2 space with respect to the rescaled reversible measure, this one. And then take a function V, which depends on X and on omega. So a generic environment omega, okay? Not that Vx depends on omega tilde, because it belongs to the space. Then we say that the function Vx weakly two-scale converges to V, and I will write shortly that Vx two-scale, Vx, okay, I will write this, if the following holds. So the sequence V epsilon, which is a sequence of a function living in, so a family of functions living in different spaces when epsilon changes, is bounded asymptotically when epsilon goes to 0. So let us say that it is bounded. And then I have this, when I take a function phi of x and I multiply for a function f of the environment, but observe centering my microscope at x and zooming out, then when I take this product and I take the product with the V epsilon and I integrate with respect to the rescaled reversible measure, so the limit in some sense forgets omega tilde, and the effect of the environment is given by this average with respect to the pan distribution. So at the end you take again the integral with respect to the Lebesgue measure times n, and then the integral with respect to the pan distribution, and here you have V x omega and then phi x f omega. Okay, so this is not free, so a special property that I isolate. Okay, and it's similar to two-scale convergence. So let us see an example, a basic simple example. So here I have reported here the definition of a two-scale convergence, and here I have recall the two-scale ergodicity. The ergodicity, this is free, it also always. And then you see that if you take the statement of the two-scale ergodicity, so fix a psi, which is continuous with compass support, and replace in the statement of two-scale ergodicity the test function phi by psi times psi, phi, sorry, then you get the following basic example, that is for almost all environments omega, given psi, given function psi, continuous with compass support in RT, we have that psi thought in this space, L2 space, two-scale convergent to psi, but now thought in the space L2 mdx times P0. Okay, so it is a very basic example. Okay, up to now, I have considered only functions, observables, but an important thing, also in standard mathematics, is calculus with the difference. Okay, is the analog of differential calculus. So I fix because then I wanted to consider the dynamics of my random walk and the random walk jumps. So I wanted to see the variation of the difference, the variation of functions along the jumps. Okay, so here I introduce the epsilon gradient. So consider a function V, it's a function on the support omega hat, which is the support of my reversible measure, but it is also the state space. Omega hat is also the state space of the random walk. Okay. Then it's, so the epsilon gradient of V is a function in two entries. One is the position, x, okay? And one, let us call, so it's another, so it's a vector, z, which I will call the jump, because at the end it is related to the jumps of the random walk. So, and it is given by this ratio. So V evaluating x plus epsilon z minus Vx divided by epsilon. So it's not something really new, in the sense that if you, so I will write by E1, E2, and so on, the canonical basis of RT. Then you see that the epsilon gradient of the function V evaluated in the position x with the jump EI is simply the standard epsilon discrete derivative of V at the point x in the direction EI, okay? So since I have random walks that can jump from one point to any other point, and there is not necessarily along the direction of the coordinate axis, I have therefore to keep this Z free, okay? It can be any vector a priori. So I don't go into the details. So okay, I wrote the definition here, but it's not, will not be essential to remember it in what follows. So what I say here is that I have a rescale measure, rescale reversible measure for functions of x, okay? But I have a natural measure for functions with the entries x and z, okay? So this is a pure point, so this nu is a pure point measure, and it is, okay, it assigns masses to points of the form epsilon a, b minus a, where a is a point in the state space and b is a point in the state space. So b minus a is indeed one of the possible jumps on my random walk. Okay, anyway, this is the natural measure for the gradients, okay, for the epsilon gradients of the function. And then I can introduce the Hilbert space, an epsilon Hilbert space, this one, which is given by the function V, which are square integrable with respect to the rescale reversible measure, such that their epsilon gradient is again square integrable with respect to the right measure for the gradients. So it's an Hilbert space, and as in the standard H1 space, the norm is given by the sum of the two norms, the norm of V epsilon and the sum of the gradients, okay? Okay, so now, in order to understand, to isolate some ergodicity property also for the gradients, I need to introduce another measure, okay, which is not so exotic indeed. So recall that I define E0, I wrote E0 for the expectation with respect to the Palma distribution, okay? So the Palma distribution is a probability measure with the support given by the environment such that the origin is in the state space of the random walk, so omega 0. So now nu is a measure on the product space environment times the group, so which can be, I recall you, G can be CD or RT, and the expectation of a function f for nu is this one. So it is the integral with respect to the Palma distribution in omega, and then you sum, so omega is in omega 0, so the origin is in the state space of the random walk in the environment omega, and then you sum of among all other points in the state space omega hat the probability rate for a jump from 0 to x, so this is R0x of omega, and then the function f omega z. So here you have the environment, here you have the jump, essentially. Okay, now I don't enter in this definition, so let us skip the details, but what I want to say is that, okay, gradients are functions in two variables, okay? And so the epsilon gradients lives in this L2 space, okay? And one can define, isolate an ergodicity, to scale ergodicity, spatial and power ergodicity property for functions in X and Z. Generic function, you can consider V epsilon of x z given by the gradient of some function u epsilon x z. Okay, and you can define also here, I don't enter in the details, you can say that this family of function, v epsilon, to scale converges to a function w, so w epsilon to scale converges to a function w, if you have essentially the property that the integral with respect to x and z for a given environment, omega tilde, when epsilon goes to 0, corresponds to an average on all the environments. Okay, so here you integrate in x and z, and in the limit you have also an average with respect to omega. So we have these three entries: position, environment, and z. We integrate also with respect to omega. So the right function is a nu of omega z. Okay, so okay, this function lives in this H2 space. Okay, I don't probably I don't have time to discuss the example. Okay, this example, but I want to state up to now I gave a definition, but now I want to arrive at a compactness result for two-scale convergence, also a structure theorem, which is the reason why two-scale convergence is at the end useful, but we have almost done. Okay, so I needed to introduce the space of square integrable forms. So I have this measure, nu, and I call the square integrable function with respect to nu square integrable form. So a square integrable form is a function of omega and z such that the expectation, so the integral, sorry, of the square of f with respect to nu. Okay, here there is an error, here there is also the weight given by the jump rate is finite. So this is nu. The effect of nu, the integral with respect to nu is by definition this. Okay. Okay, and then now, okay, I have these forms and I want to distinguish between potential forms and solenoidal forms. So recall that omega 0 are the family of environments omega such that the origin belongs to the state space of my random walk. So if I have a function u, I want to define a gradient, but now not a gradient of spatial functions. I want to define a gradient of function that depends on the environment. So let us take a function u, which is u of omega. I want to define its gradient. So it's again a function in two entry, but now the first entry is the environment, and the second entry, let us say, is the jump, is z. So the gradient of u, evaluated in omega z, is given by the function u observed in the environment center at z. So you translate in order to center at z, minus u of omega. Okay, I don't discuss, but there is a relation between this gradient and the epsilon gradient, but I don't discuss the link. And now, okay, we have the analogous of Weil decomposition. So I take the space of square integrable environment forms. So it is given by the function of environment and jump integrable, square integrable with respect to nu. And I can express this. Express this H2 space as an orthogonal sum of two subspaces. So one is the space of potential forms, okay? So A2 pot of nu, which is the closure of the gradient of u when u is bounded and measurable. So u is u of omega. So these are the potential forms, similar to the classical definition of potential vector fields. And then the solenoidal forms, the space of solenoidal forms is its orthogonal subspace, okay? So this is an orthogonal decomposition. I have to say that there is, it's simple to, so you have integration by part, and you can indeed introduce a divergence in this setting, such that if you integrate a potential form in the form gradient of u times another form v, this is also equal to minus the integral with respect to the Pound distribution of u of omega times, okay, an operation on your form v, which is which we call the divergence of v. So at the end, we have this this characterization that a form is solenoidal if and only if the divergence is 0. Okay, will be useful in the next talk. Okay, I have almost done. Okay, now I introduce the homogenized matrix. So it lives in this abstract space of square integrable forms. Given a vector A in Rd, I consider a deterministic, a very simple form, UA, in the entry environment jump, which is simply A times scalar product with Z, so it does not depend on omega. And I consider the following quadratic form. To each vector of Rd, take the form UA, take its solenoidal component and compute its norm square, okay? So times 1/2, okay? So this is a quadratic form, so you can write, so it's a quadratic and non-negative, and therefore there exists a unique D times the symmetric matrix D, such that this form is equal to the vector A times the scalar product with dA. So this is the scalar product in Rd. Okay, this is the homogenized matrix, and it will be appear in plenty of it appears in plenty of applications. Okay, I skip this, but what I want to say is this result. Okay, so why two-scale convergence is important? It's important because there is a compactness property, and it's the following. Okay, it's even more general, but in the applications that I will discuss later, so in the next talk, we will deal with families that are families of functions that are bounded in the H2 space. I recall you, this is the set of function V, which are square integrable with respect to the rescale reversible measure, and such that also the epsilon gradient, so this is the spatial gradient, is square integrable with respect to the right measure. And then there is this theorem. It's the following, that for almost all environment, indeed for all environments in a subset given by the so-called typical, let us say typical environment, which has a full measure, the following holds. So if the environment, if you fix an environment omega tilde in this nice set, which has full probability. So take a V epsilon, a family of functions parameterized by epsilon, which is asymptotically bounded. Okay, so they live in different spaces, but okay, their norm, so the norm of these functions is bounded when epsilon goes to 0. And then along a subsequence, you have that your function, the epsilon of x, to scale converges to a function. So you have this empower to scale ergodicity, which holds for this function v epsilon of x, and the averaging in the disorder in the environment omega is codified by this function vx omega. But not only, we have also that along the subsequence, also the gradients, the epsilon gradients, to scale convergence to a function. So since in the two-scale convergence, at the end, I average M on the environments, here I have that this limiting function depends on omega. But now, okay, and I conclude, so you can ask also a very ambitious question. Okay, this is one of my songs. So how do V and W look like? Indeed, they have a particular structure. They are not arbitrary. And there is this structure theorem. So when is the following. So I stated when the homogenized matrix is non-degenerate, and it's the following. So take so your fix an environment which is typical. So when and therefore you have the compactness property I told you. for family V epsilon, which are bounded in this in the H1 space. So for each epsilon, you have a function in this space, and their norms are bounded asymptotically when epsilon goes to 0. And then, I said before that the V epsilon of X two-scale converges to a function, but indeed this function, we know, does not depend on omega, and moreover is in the standard H1 space of RD, okay? The standard H1 space. While the gradients, we know that along a subsequent two-scale converges to a function W, which is a function of X, the environment, and the jump, and it has this special form. So it is like the elementary forms I introduced before. So you have the gradient of V in X, so the gradient of this function V times Z, plus an extra term. So you have a function W bar in X, Y, Z, such that when you fix X, you have a potential form, okay? And okay, it is more complex, okay, when, okay, we discuss later. Okay, no, let us, and then I really conclude. So when the matrix D is not, not degenerate, then you have to make some small changes, some modification. So since the homogenized matrix is symmetric, you can diagonalize, and we can assume that the first D-star entries are positive and the other are 0. Then instead of dealing with the standard H1 space, I consider H1 star, which is given by the square integrable function with respect to the back that have a weak derivative, which is integrable in the first D-star coordinate. And I consider also the gradient of F restricted to the first D-star coordinate, and then for the other coordinate is 0. Then I have the same result as before. The only thing is that the limiting function V is in H1 star, and I have to replace the gradient of V with this gradient in the first D-star coordinate. Okay, this structure theorem appeared already in the papers of for homogenization of differential operators. There are several papers of Zhikov, also random differential operator, Zhikov and Piarnitsky, and the proof of this theorem for in the present setting is given, okay, in a preprint, okay, it appeared, a preprint of mine, it appeared before, and the technical difficulties here comes from long jumps, the presence of long jumps. So I would stop here this presentation of two-scale convergence. So if there are questions.
Okay, thank you very much, Alessandra. So if there are any questions, you can unmute yourself and ask.
The next page is example. Is possible to show example?
Yes, okay. Yes, the example are the following. Okay, I tell you one property, but it's simple that I need for the example. So I told you that the homogenized matrix D is defined in this way. You take a vector A, you consider this deterministic trivial form, elementary form, A times Z, it does not depend on omega, and you compute the norm of the solenoidal part of this form, okay? So the fact that DII is positive means simply that these elementary forms with respect to the first D-star coordinate are not purely potential, so they have a sign, so this is not a 0. While the fact that the other diagonal entries of the homogenized metric are 0 means that these elementary forms are potential. So the example, which is the trivial one, because the interesting examples come from nature, from application, is the following. So take V epsilon of x, simply a regular function of x psi, but okay, in this case, so you think of psi as an element in A2 of the rescaled reversible measure. Then we know, I said, we know that I commented before, V epsilon x to scale converges to psi itself, okay? It is not difficult to check that the epsilon gradient of psi, okay, to scale converges to the standard gradient of psi evaluated next scalar product with the z, okay? Then let us see that we have indeed the structure theorem. We have that V epsilon converges to a function psi, okay, V psi, which depends only on x, and this is true. So this psi is in this H1 space, and that is true. But look at the gradients. So the limit of the gradients is this, and you can split. So you can take here the projection of the standard gradient on the first d star coordinate, okay? So, and then you take 0 times z, and then this is the other part, okay? And because of what I told you before about the zero entry of the homogenized matrix, we know that all these elementary square integrable forms are purely potential. So at the end, this part here is this one. And the potential part for a fixed x is this one, okay? So this is the trivial example, but applications give much more interesting examples. So solution of differential operators, difference operators.
Thank you.
Okay, I hope. Okay, I hope it is clear.
So is there any other question? So if not, let's thank Alessandra for this first lecture. Okay.
Thanks.
So I think we can take maybe a minute or two break, and then I don't know, Alessandra, do you want more time for a break, or? Can you hear me?
I hear. I didn't. Okay, I hear. I do not know if the question was for Milton. I didn't understand.
Okay.
Oh, no. So I'll share the second half. So the question was just whether you need more of a break than a minute or two.
No, for me it's okay. It's for the problem can be okay maybe for other people. So for me it's okay.
All right, so we'll wait like another minute or two. Give people a moment. And Alessandra, do you have a link to a Dropbox link to the slides that you could share in the chat, or?
Now I don't have the slides in Dropbox. Do you want now the slides?
Well, it's useful. It's nice because people can then look back at stuff.
Okay. Anyway, I will repeat the basic definitions. I don't have. I have not prepared a link.
Okay. No, that's fine.
I can do it now, but maybe. Anyway, I will recall the notation that I need. I hope.
Okay, so maybe we'll get started now. So I'm just going to set it so that people stay muted until the end of the talk. So it's a pleasure to have Alessandra speaking to us again on this same subject. So she'll continue her talk and take it away now.
Okay, so thanks. So now I will discuss about applications of this two-scale convergence. Up to now, maybe it has appeared as something a little abstract, but the real interesting examples come from applications. So I will discuss application to invariance principle, homogenization, hydrodynamics, and I think I will have no time for resistor networks, but okay, people interested can then see the slides. Okay, here I have just recalled the general setting. So these slides were also present in the talk one. So I have my random walk xt omega. The objects are given by a probability space. Omega is the space of environment. Then I have the group G, which can be ZD or RD, and the group GX, both of omega, the probability space, and on RD. And for simplicity, the action on RD is the trivial action by standard translations. Okay, then a fundamental object is mu omega, which is a pure point measure, okay? The support of mu omega is indeed the state space of my random walk. It's given by these red points. And I have also, as other object, the jump probability rates of my random walk with x and omega and y in the state space omega at r, x, y. Omega is the jump probability rate in the environment omega. Okay, for simplicity, I recall you that when G is a group ZD, as for the simple random walk in the supercritical percolation cluster, I suppose that the state space is inside the ZD. Okay, just for simplicity here. And then I have so general assumptions to cover a lot of models. So the law of the environment is stationary and ergodic for the action of the group. The random walk is irreducible. Then I said that mu omega is a reversible measure for the random walk. Then the intensity of my reversible measure, so the expected mass of a given box of the unitary box is finite and positive. Then we have the covariant relation, say that all these objects are intrinsic. And then some moment conditions. I don't enter in the details, but these are some type of second moment conditions. And then, okay, it's something technical, H2 P0 is separable. Okay, a first application in discrete probability of the two-scale convergence is due to Pierre Mathieu and Andrei Piatnitsky in the field of quench invariance principles. So they discuss, so they applied this two-scale convergence in particular for my first example in the previous talk, so the simple random walk on the supercritical percolation cluster. So the same result in quench invariant principle was obtained also by Berger and Biskup by other methods, almost so at the same time. And in both cases, a fundamental idea is the idea of the corrector field, which goes back to Coe's law. Okay, let us first state the quench invariance principle. So he says the following. So first of all, they wanted to fix a starting point for the random walk. So it will start at the origin at time 0. So you need to restrict to environments omega such that the origin is in the infinite cluster. Okay, this is the simple random walk on the infinite cluster of the bond percolation. Okay, take omega in this space, and then for almost all omega, sorry, in omega 0, with respect to the Palm distribution, you have the diffusively rescale random walk. There is also omega, sorry. The diffusively rescale random walk converges to a Brownian motion with the diffusion matrix, which is 2D, and D is our abstract object introduced with the square integrable form. So D is the homogenized matrix. Okay. So note that P0 is the Pan distribution, but in this case it's simply the original probability condition to the event that 0 is in the infinite cluster. Okay. Now recall that I had introduced just at the end, I had introduced, not at the end, also at the end, I discussed them, some elementary square integrable forms. So given A in RD, I introduce UA, a form, so a function of the environment omega and of the jump Z given by A scalar product with the Z. So these are vectors in RD, I take the scalar product. So this is a square integrable form. So now take, so we know every form has a solenoidal component plus a potential component. So let us define GA as minus the potential component, so minus the projection of UA on the space of potential forms. Therefore, UA plus GA is solenoidal, okay? And recall that the homogenized matrix has been defined in this way. So it's the symmetric matrix such that when applied to the vector A, scalar product with A, you get the norm of the solenoidal, the square norm of the solenoidal component of this elementary form UA, okay, times 1/2. So therefore, A scalar product dA is 1/2 this square norm, UA plus GA. Okay, and then a fundamental object is the corrector field. So the corrector field is the following. So it's a function of the environment, okay, omega, and also of X, which is a point, a possible state for my random walk. So X belongs to omega hat, and it is defined implicitly. So in this way, we require that for a fixed environment omega, the variation of the corrector field, when you go from X to X plus Z, okay, and X plus Z are 2 points in the infinite cluster, scalar product with A is given by this potential form, GA, is given by J, evaluated in the environment omega, center at X, and the jump Z. Okay, it's an implicit definition, but indeed the corrector field exists. You obtain the corrector field by integration along that path. So you start from chi, so you have to think as omega fixed. Then you know that the origin is in your cluster, and then to define so chi here. So if you take, for example, here the value 0 to define chi in omega E1, it's enough to apply this formula, and so on. You can take, define at the end the corrector field by integration from the value at the origin. This is for a given omega. And since GA is a potential form, so it's a gradient of something, so the result is path independent. So this integration is moral, is legal. The only thing, pay attention that this corrector field is well defined apart, so uniquely defined apart an additive constant, if you want this, so the value of this function, key of omega 0. Okay, and now let's see the machinery of corrector field in action. So by definition, GA is such that UA plus GA, UA of omega Z is A times Z, is solenoidal. So it's a solenoidal form. And as I told you in the first talk, solenoidal is equivalent to say that its divergence is 0. But the property to have a divergence 0 is equivalent, for the definition of the corrector field, is equivalent to the fact that given omega, for almost all realization of the environment, the function, the observable on the state space of my random walk, given by X plus the corrector in omega X, is harmonic. So this is the generator of my random walk. And this implies, in particular, can be restated in this form, that if I read this function here, which for a fixed omega, along the trajectory of the random walk, I have a martingale. And having a martingale, you can apply, so all the conditions are satisfied here, the invariance principle for martingales, and you get that, therefore, the rescaled, diffusively rescaled object, this one, satisfy an invariant principle with diffusion matrix 2D. Okay, so the problem at the end, also in the paper of Biscoe and Berger, is to show that this correction here, so it is called corrector because it's a correction in order to have a martingale. This correction here is negligible, and then if you can neglect this, you get the invariance principle, the quench invariant principle for the random walk. So in the case of Mattia Piarniski, in their paper, they use the two-scale convergence. So I don't give all the details, but the fact is that, okay, they consider, so you want to prove that this one is negligible. You consider a rescale function. You rescale. Up to now, we have seen things in the microscopic world. We want to have a limit, so we rescale. We have to zoom in. So we have the rescale corrector, which is given by this expression. And then thanks to it kernel bounds, it's enough at the end to show that the L2 norm of the rescale corrector restricted to the unitary box, let us say, goes to 0. And indeed, the corrector, for the corrector, you know the epsilon gradient because it has been defined in terms of the differences of the corrector. So using the Poincare inequality and the definition of the corrector, which is essentially this, they show that the rescale corrector center, so minus a constant depending only on omega, okay, so this function here is a bounded, so when you vary epsilon, you have a family of functions, and this is a bounded family in the H1 space. So we are exactly, so this is the first non-trivial example where you can apply, so non-trivial example in my discussions, when you can apply the compactness structure theorem I gave you before for bounded families in the H1 space. And so they apply it to scale convergence, so the structure theorem and so on. In order, so I also other ideas, I think again the Poincare inequality in order to study the limit of the rescale corrector center and of the centering, and they show that they goes to 0, and so they were able to conclude and to get the quench invariant principle. So this is a first application. So now I discuss another application which is given by the massive Poisson equation. Okay, again, as in their case, but now I come back, but I have to say what the discussion I said before, I refer to their model, so the random walk on the supercritical percolation class, but my language was general, so these arguments are completely general. So the discussion I give now is for the general setting, so not only for the supercritical percolation cluster. So I interested to the diffusively rescaled random walk, okay? So epsilon is my scaling parameter. Here I accelerate time and I zoom in space, okay? I recall you that I introduced the rescaled reversible measure. And it is convenient to give a name L epsilon omega for the Markov generator, which is a difference operator, the Markov generator of the diffusively rescaled random walk, okay? So it's a difference operator. And, okay, trivially this is, so if I take a minus, the Markov generator, this is a non-negative self-adjoint operator in L2 of the rescaled reversible measure. So given a number lambda, a positive number lambda, you can invert the operator, which is strictly positive, lambda minus the generator, and it is well defined, okay, in the L2 space. Okay, as a consequence, for each f, for each function f, which is square integrable, you have a unique solution, unique strong solution U of the massive Poisson equation, which is the following: lambda of times U minus the generator of the Risqué random walk in U is equal to F. Now, you can give also a weaker formulation of this massive Poisson equation, because there is there is an integration by parts property. So essentially, you can this is if G is equal to H, this is the Dirichlet form. But let us take two nice functions, G and H. If we compute the scalar product in the L2 space of the Risqué reversible measure of G and minus, the Markov generator applies to H. So this is equal to 1 alpha, and then we have the scalar product of the epsilon gradient. So we come back to the epsilon gradient, we forget the generator, we come back to the difference calculus as before. So we have the scalar product of the epsilon gradient of G with the epsilon gradient of F. Okay. Maybe you hear some noise of kids. They are not my kids, but there are kids in the building. Anyway, okay. So we have this integration by parts formula. And therefore, the weaker formulation by integrating against the generic function V is the following. So U in the H1 space, which is as before, is given by the function U, which are square integrable with respect to the reversible measure, and also the gradient is square integrable. So is a weak solution of the massive Poisson equation if for each test function V in this special H1 space, you have this identity. So I just restated this in weak 4. Then by the Lax-Milgram theorem, the weak solution exists and is unique, and therefore it coincides with the strong solution. So we have two ways to characterize the same U, okay, the U solving the massive Poisson equation. Okay, now I want to state the limiting behavior, both of the solution of the massive Poisson equations and also of the gradients of its epsilon gradients. But so I needed to recall some definition of my talk number 1. So recall that it costs to change coordinates. Since D is the matrix, the homogenized matrix D is diagonal, we can think, so it can be diagonalized, we can think D as diagonal, and we order the canonical basis in order to have the first D star diagonal entries of the homogenized matrix are positive and the other are 0. Okay, they could be also all positive, it could be non-degenerate as well. So I introduced the space H1 star, which is given by the function in L2, in the standard L2 space of RT, having a weak derivative in the I coordinate in L2 when I goes between 1 and D star. And then the gradient star of f, of a function f in H1 star of RT, is simply the standard gradient for the first D star coordinate, and then you have 0, 0, 0, 0, 0, okay? So now fix, let us, so lambda is always a fixed positive number. Now I consider the massive Poisson equation, and I call 1 for each epsilon, the scaling parameter, and I call f epsilon the known function, okay? So given f epsilon, I call u epsilon the unique weak solution, a strong solution is the same of the massive Poisson equation. as we will see the limiting equation at the end, the macroscopic behavior will be described by the following one. So lambda u minus the divergence of the matrix D applied to the star gradient of u is equal to f. Also here you can introduce a weak formulation, and by Lax-Milgram theorem there is a unique solution in this space H1 star. Okay, and then this is the theorem that I will apply it to hydrodynamics soon. Okay, so recall that we have F epsilon in H2 or mu epsilon. So the rescaled, this is written also here, sorry, the rescaled reversible measure. U epsilon is the associated solution of the Poisson equation. And then we have, for a given f, a square integrable, a bag square integrable function. We have u, which is defined as the solution of the effective Poisson equation. Okay, so when omega is in the set I introduced in the previous talk of typical environments, which is a set having full measure, for each lambda and for each data, f epsilon, given f epsilon is indeed a family of data, one for each epsilon, and f, we have the convergence of solution and fluxes. So I will specify the meaning of this convergence. So if f epsilon converges weakly to f, then the solution, the macroscopic solution of the Macy-Poisson equation, u epsilon, weakly converges to u, and the epsilon gradient of u epsilon weakly converges to the gradient star of u. And all these convergences become strong if f epsilon strongly converges to f. And in this case, we have also the convergence of the so-called energies. So if I take this is the Dirichlet form essentially of u epsilon, but we want only to deal with difference calculus. So if I take 1 alpha, the norm of, the epsilon gradient of u epsilon, okay, square, then this converges to the integral with respect to the Lembeck measure of m. So this star gradient that looks only at the first d star entries of ux, times scalar product, the diffusion, the homogenized matrix D applied to this gradient. So before I introduce so the two-scale convergence, this convergence here is something more rough, okay, because it does not look, it's similar, but it does not look similar in some sense. It does not look to the environment. That is, okay, similar in the sense you take a test function. So let us see the weak convergence. So if I have a v epsilon, which is a function in L2 for the rescaled reversible measure, and I have a v, which is a square integrable function, then we say that v epsilon, I have a v epsilon for each epsilon, weakly converges to v if the family v epsilon is asymptotically bounded. And moreover, when I take a nice test function, so phi, which is continuous with compact support in RD, so the scalar product between v epsilon and phi in this space, L2 of the rescaled reversible measure, converges to this other scalar product. Okay, so you have this. Okay, and you can give also a definition. You have the definition in order to have the stronger convergence. Okay, here there is no omega. All tests you play only with test functions that are function of the position of x. Okay, why it is relevant? What I said in the first talk also here. So the compactness and the structure theorem. Because of this simple observation, which is very common indeed when studying, okay, the Macy-Poisson equations. So in both cases, I had two cases. When the data, when f epsilon weakly converges to f, and the stronger case when f epsilon strongly converges to f. In both cases, when you have this convergence, the family f epsilon is bounded, asymptotically bounded. Okay, now if you use the weak formulation, the massive Poisson equation, you get, taken as function v here, exactly your solution u epsilon, you get that you can bound the norm of the H1 norm of u epsilon in terms of the H2 norm of f epsilon. So you have simply to use Schwarz inequality multiple times. Okay, but since these norms are asymptotically bounded when epsilon goes to 0, we are back to the proper, so we are dealing with a family of functions. So the solutions u epsilon are a family of functions bounded, asymptotically bounded in H1. And therefore, one can use the compactness structure theorem I gave before. Okay, this is not enough. Then you have to play in order to understand what is U and what is this correction of V bar. Okay, you play, it means that you have to take this weak characterization of the massive Poisson equation and plug in clever test function V. Okay, and then you start to understand the structure of these limit points. And the limit points is unique, it does not depend on the subsequent, it's unique for all subsequences epsilon n. Okay, there is, then when you have the convergence of the massive Poisson equation, then you are happy because you have a lot of gadgets for free, okay? And you have the convergence of resolvents and semigroups. So in some sense, we get a weaker form of central limit theorem. So let us see. I recall you my object, dynamical object, so stochastic process is the diffusively rescaled random walk in the environment omega. So given lambda positive, lambda minus the generator, and then inverted, this is the resolvent, the so-called resolvent of the random walk. And we call it, as usually is done by the letter R. So it depends also on lambda, lambda is fixed. And then I denote by P, a time T, okay, and then there are also epsilon omega. So the Markov semigroup at time T for the diffusively rescaled random walk. Now let us move to the asymptotic object stochastic process, which is the Brownian motion with diffusion matrix 2D, and D is the homogenized matrix. So I call R lambda is a resolvent, is NPT the Markov semigroup. So the massive Poisson equation is simply an identity concerning the resolvent. So U epsilon is the solution of the massive Poisson equation with entry with the data F epsilon, if and only if U epsilon is the lambda resolvent applied to F epsilon. Okay, so the homogenization theorem I gave before implies, so immediately, so it's this corollary, that you have the convergence, so given a function f which is continuous with compact support, the epsilon resolvent applied to f strongly converges to the resolvent, the resolvent of the Brownian motion applied to f, okay? And okay, this is almost immediate from the homogenization theory. Then there is a result of Pastukov, also in a paper of Zhikov, that tells you that when you have this also for each t, time t, and for each lambda positive, when you have the convergence, this form of convergence of the resonance, then you have also the convergence of the semigroups. In that sense, here we see a weaker form of a central limit theorem. Okay, indeed, if you assume something more on the environment, we have also stronger forms, always weak, but stronger forms of convergence of the resolvent and of the semigroup. And these other limits are relevant for hydrodynamic limits. So the condition is the following. So mu omega, I recall you, is the reversible measure for the random walk. Okay, so let us divide it RD in boxes. okay, unitary boxes, and this is one. I consider the unitary box 0, 1 to D plus K, where K is in ZD. So suppose that one of the following conditions is satisfied. So the first one, which is very good when you play with lattices or sets inside. So when omega hat is inside ZD, you are right, or some other lattice is immediate. It's almost immediate. You have that. So the mass given by the reversible measure to these boxes is uniformly bounded. It does uniformly in the boxes. And the other condition, which is alternative, is that these masses have covariance that decays in the distance, at least as k minus k prime, so the distance minus 1. Okay, just okay, I don't have to insist on this point. And now we see an application of this, or exactly of this theorem, to hydrodynamic limits. So we change also, maybe it's also good to change perspective and also in some sense a subject. So now I consider, I want to talk about hydrodynamic limits of interacting particle systems. Okay, and apply the previous results. To do this, I need to restrict to symmetric jump rates. So I will assume that the probability rate for my random walk to jump from X to Y is equal to the probability rate to jump from Y to X. Therefore, okay, my mu omega here, the reversible measure, is simply the counting measure on omega hat, which is the state space of the random walk. So the results I have concern spatial interacting particle systems, which are given by considering multiple random walkers as above, as before, but with an additional interaction, so they interact, and we can consider, I can deal with two forms of interactions. One is the so-called R-chord interaction, okay, and then we have the exclusion process on omega hat. The other interaction is the zero range interaction, and then the resulting process is the zero range process on omega hat. Okay, these results. I will talk. I will focus on the exclusion process, yes, because of okay, time is, since the time is limited. But okay, and it is not. So the results will appear in a forthcoming, hopefully preprint. Okay. So maybe not everybody is familiar with exclusion processes. I fix. So I explain exactly what I mean. So omega is my environment. Okay, the configuration, so recall omega is the environment, and then to each environment we associate omega hat, which is the state space of my original random walk. So it is a countable subset of RD. Okay, and then I have my particles. Sorry, in my picture, so the points are in red. So these are the physical points where particles can lie. So a configuration of my exclusion process is described by eta. So eta is an element of 0, 1 to omega hat with this interpretation. If the occupation number, so eta x is equal to 0, then the site x is empty, is not occupied by a particle. For example, this one, there is no particle here. While if eta x is equal to 1, then the site x is occupied by a particle, and particles are blue. Okay, are colored by blue. And then each particle behaves as my original random walk. So in particular, so at least each particle wants to behave as the original random walk, but there is a constraint. So let us see. So this particle, let us focus on this particle in X. So this particle waits at a certain moment with the probability rate given by Rxy, attempts to jump at the site to the site Y. So it attempts. So if the site Y is empty, then it jumps. But as in this other case, if the site Y is occupied by a particle, the jump is suppressed. Okay, so this is the exclusion process. To be rigorous, okay, one can also write the Markov generator. So you have the sum. So given a function of eta, eta is an element of 0, 1, omega hat, the family of occupation numbers. So the generator, which depends on the environment omega, applied to the observable F, is given by the sum with x in omega hat, sum with y in omega hat, and then we have the probability rate to jump from x to y times this term factor which encodes the hardcore interaction. So eta x times 1 minus eta y. So this is 1 only when you have a particle in x and 0 particle at y. And then here you have the variation of f before and after the jump of the particle. So this configuration, eta xy, is the configuration that you obtain by exchanging the occupation value in x and y. So, so this configuration in z is equal to the original configuration in y if z is equal to x. This configuration in y is equal to the original configuration in x, and for the other sides, nothing has changed. So if you want, you can think of the exclusion process as also as an exchange process. So for each unordered pair of sides, x and y, you consider, so the generator is the sum among the unordered pairs, x and y, of the jump probability rate from x and y, and then this difference. Now we have at this point to make some assumption, because it's not obvious that the exclusion process exists. So there is a naive graphical construction. Okay, you can think to construct graphically the exclusion process in this follow. So for each pair x and y, an ordered pair of sides x and y, you attach to each another pair x and y in omega hat a Poisson process, okay, a Poisson process with the parameter with intensity the jump probability rate between x and y. So all these processes are independent between them. And the idea is that when, so if you consider, for example, the pair x and y, when your Poisson process increases or 1 unity, so when it jumps, then you exchange the value occupation number between eta x and eta y. So, okay. So this is naive because in this, so it's rather, there is a fundamental problem because we have infinite points, infinite edges, infinite Poisson processes. So when we want to apply this algorithm, apparently, so this algorithm, the problem is that, so we start at time 0, but there is not a first time, positive time where some Poisson process have jumped. So the jump time of the Poisson processes, the jump times of the Poisson processes is a dense set because we want to control all these Poisson processes. So to solve this problem, there is an assumption which is very natural, as also interpretation in terms of percolation. So in order to build, to formalize the previous construction with Poisson processes, we need the following assumption. So we assume that for some time, T0 positive, so there exists T0 positive such that for almost all realization of the environment, the random graph with the vertex set given by the sites where particles can lie, and edges given by the pairs, another pairs, such that the associated Poisson process had already one jump, as almost surely only connected components with finite cardinality. And this is nice because up to time t0, it's true that we have infinite Poisson point processes, but at the end we have finite clusters, and then in each cluster we can apply the previous definition. Each cluster is finite up to time 0. We can focus on finite islands. They do not interact in some sense, and then we can island by island construct the exclusion process, and then after time t0 we can start again. So this assumption is to have a well-defined process, and then in order to use the results, the strong results on convergence of resolvents and semi-groups, I make also the same assumption, the previous theorem, okay? Concerning here, so in this case, since the counting measure is my reversible measure for the random walk, the previous variable nk as a simple form, they equal to the number of sides in the box, unitary box associated to k in CD. Okay. Now, in order to state the hydrodynamic limit, I have to introduce the fundamental object, the right object to state the hydrodynamic limit, which is the empirical measure. So again, we have two pictures. So we have the microscopic world and the macroscopic world. The macroscopic picture, the world is the same, but the pictures are different. So here you see my system of particles. The blue circles and the red circles are sites that are empty. And here I have zoom in the previous image. So I have again a rescaling parameter epsilon, which is positive, and given eta, so my particle configuration, I associate in the macroscopic world essentially the so-called empirical measure. So the empirical measure is a measure on RD, which depends on eta, and it's built in this way. So you have first to rescale the length by epsilon. So if this is one, if this is one, then this is epsilon. So you have to rescale length. Okay, maybe it's better to take it out. You rescale length. Okay, so point x becomes epsilon x. Okay, and then to each particle, so when eta x is equal to 1 to each particle, you associate a Dirac measure in epsilon x with weight epsilon d. Okay, so the sum of these, the combination of these weighted Dirac measures is the empirical measure associated to the particle configuration eta. So in what follows, I will write a pi epsilon eta of phi for the integral of my function phi. Phi is a function of x, of the position, with respect to the empirical measure. Okay. And then I can state the hydrodynamic limit. So we have a very general setting. So we have a very general setting for the random walks. And I made two assumptions. One, which is necessary to have a well-defined exclusion process, and another assumption, which allows me to invoke the previous theorem on convergence of resolvent and semi-groups. So I state the result. So in what follows, given P omega m is the law of the exclusion process with initial distribution m, which is a probability on the particle, on the configuration space, so 0, 1 to omega hat. Now, take omega, which is a typical environment. Okay, so almost surely omega, if you take omega, so it is typical. Okay, and then fix. So for each omega, which is typical, you have this nice property. Fix a profile, so a function rho 0 from RD to 0, 1, which is, okay, Borel, measurable. And then for each epsilon, your initial distribution M epsilon has this property. So it's a probability on the particle configuration space, and you have that with a high probability, the empirical measure, the epsilon empirical measure, is a good approximation when epsilon goes to 0 of the profile rho 0 x dx. So this is a particle distribution in the continuum, while pi epsilon eta is a measure, poor point measure on RT, and it's random. It depends to eta. But for the initial distribution, these two objects are very near, better and better as epsilon goes to 0. Then, if you can take you fix a time observation, an observation time, capital T, then the same holds for the empirical measure at the time epsilon squared T, that is. You consider the exclusion process, but in order to see something at the macroscopic level, you have to accelerate the dynamics. You take, so eta evaluated at time T times epsilon minus 2. You consider the empirical measure at this time, which is random, and you evaluate it, you take the integral, you evaluate the integral of your test function phi. Then this integral is very near to the integral of phi, the test function, with respect to a macroscopic profile, rho xt dx. And this approximation is good uniformly with the time varying in the time window of your observation. So this limiting profile, rho xt, is the solution of a differential equation, partial differential equation, where again you get the homogenized matrix. So you have the time derivative of rho is the difference of the homogenized matrix D times my gradient, okay, gradient star if D is degenerate, applied to rho. And the initial profile, so this is a Cauchy system, is given by rho 0. Okay, and I make some comments. So this example, this interacting particle system is an example of non-gradient interacting particle system, because if you compute the infinitesimal current between two sides from x to y, so the flow particle from x to y minus the flow particle from y to x, this current cannot be written like an observable h at the configuration eta translated by x minus an the observable h in eta translated by y. You don't have this algebraic property, and the system therefore is called non-gradient. And usually non-gradient systems have a very heavy, can be solved by using a very heavy machinery, very sophisticated, and there has been one of these probability seminars by Sasada and co-workers about non-gradient systems. Okay, so it was clear that the machinery was very sophisticated. But one can avoid this heavy machinery because of a duality relation, is this one. So if you take the generator, if you take the generator of the exclusion process, apply to the integral of a test function phi with respect to the empirical measure, and you rescale it, then this is equal to epsilon to d, the sum with x, a possible site in my state space, the occupation number, eta x, and then the generator of my original random walk apply to the function phi rescale, so in epsilon x. Okay, And just to finish, I have to point out that the first person observing this, which used this duality relation in order to study the hydrodynamic limits of spatial symmetric exclusion process was Nagy. Indeed, she used not homogenization, but a stronger result, a quench invariance principle. And then in a paper of mine, I showed that indeed to get the hydrodynamic limit in a special case, okay, it was not a general as the present setting. It's enough to have homogenization, not a quench invariance principle, which is usually something very harder to get. As I told you, of homogenization, I've used the convergence. Indeed, if you use the convergence of semigroups, of the rescale random walk to the semigroup of the Brownian motion, you get the hydrodynamic limit only for a fixed t. So you don't have this control uniformly in the time t inside your time window. But if you use the limit of the resolvents, and not only, you have to use the limit concerning the convergence of resolvents, but also a tricky method, the so-called method of correct empirical measure, which was introduced by Goncalves and Milton Hara. You get the hydrodynamic limit uniformly in T. This method allows to get the so-called compactness, tightness of the empirical measure. Okay, there are now also other methods that works also for time-dependent rates, but this one was strong enough. Okay, I would say because of time, I would not touch the other application concerning random resistor networks, but in the slides, I will leave the slides with a full discussion of the limited conductivity of a special network, which is the Abram-Miller's random resistor networks, which is important to study electron transport semiconductors. And this limiting conductivity is again described by the homogenized matrix, D. So I would finish here, okay, also because time is finished.
Okay, so people are now able to unmute themselves. So if you want to unmute and join with me in applause for these two talks.
Okay, thanks.
So we do have time if people have questions. So again, just feel free to unmute yourself and ask your question. So maybe I can start with a question. So you were dealing in the interacting particle systems with symmetric interactions. Does any of this sort of machinery work when you deal with weak asymmetry or things?
That is in general, if you break the symmetry, no, and also the equation is different. So also, the equation is different. You have that the limiting equation. Okay, div or okay, let's write it. You have the diffusion matrix depends on the profile. Okay, in general. Then so if you add no, this is an integration. For example, if you add a very weak asymmetry, I don't know. So I didn't try yet. Maybe Jara, he has worked a lot of on also the asymmetric case. Maybe he has some ideas, but okay, I didn't check. So it is a possible direction of investigation.
There were two questions in the chat. I'll read them to you.
Mm-hmm.
Can such two-scale convergence approach be generalized outside of random walks? And is it possible lead to n-scale convergence? Those would seem like logical generalizations.
So I didn't hear the second part.
It's about whether there's an n-scale convergence result.
N-scale. That is here at this. So sorry. So for the first part, I have to say two-scale convergence for random walks in the random environment is just one stage, because two-scale convergence was applied to differential operators, random differential operators, also on a singular structure, and then this is another application. So therefore, there are examples, and historically they became before. And at this level, the important things that emerge in the limit are observable and their gradients. Maybe n. So the fact is that, okay, I don't understand. So, okay, I didn't see example with where you have n scales. I didn't see examples. That is, in homogenization, I've always seen 2 scales. So the macroscopic and the macro, macro, okay, I prefer Italian, macro, and micro, let us say, in Italian style. But it maybe one can think of systems where you have some mesoscopic scales.
There's another question from Amanda Turner. Can you strengthen the topologies in which you get convergence, i.e. larger classes of test functions?
Of larger classes of test functions? But for what? For hydrodynamic limits, or okay, in the case of hydrodynamic limits, for example, I work with continuous continuous function with compact supports, because indeed I have this case can be, I have in mind the topology, the back topology. So if you think to the back topology in the space of measures, so locally finite radon measure on RD, this is the natural one. But not in my results, but for example, in the paper of in the paper I cited before, the paper Reddick, Sada, Sao, they consider functions that decay fast to infinity. So you can also consider other larger test functions.
So there was one case I was thinking where you used the integration by parts, I think. So you needed some differentiability. I think it was quite early on in the talk.
No, but can you speak slowly?
Sorry. You had one example where you used integration by parts. So yes. You needed differentiability of the test function.
I have integration by parts. Sorry,
It may have been the end of the previous talk or the beginning of this one. This one that you have here. Yeah, the slide just one above.
Yes.
Yeah. So you used integration by parts over here. So could it have worked if you didn't have differentiability of your test function there?
Okay, I didn't understand well the final part of the question, but you can so you can work with Dirichlet forms, and this is okay the most general structure if you want. So this is a Dirichlet form. You can you can use the theory of Dirichlet form to deal with this contribution. Maybe I didn't understand well the question, but.
No, thanks. I think I probably misunderstood something. Okay, thank you.
Okay. Any other questions?
So, Alessandra.
Yes.
So I was thinking, I saw somewhere something that people sometimes call local ergodicity. So let me explain you with a quick example. So imagine that let's say that you take the Delaunay random walk, okay, so you throw a Poisson process and you move with the Delaunay on the Delaunay, how is called this thing? Yeah. So then you can imagine that when you throw your Poisson process, instead of throwing it with a uniform measure on RD, you make this measure depends on epsilon. And you assume that this measure depends on epsilon and converges in your setting to some nice measure. And then you can ask whether you also have, so you see it's like so now you have like a triple instead of a pair of guys converging in a, and so sometimes the people call that local ergodicity, because it's like the Poisson process is locally ergodic, but it's not completely ergodic because it's not really invariant under the full group, no?
The Poisson point process, so it's ergodic with respect to the action of RT. So if you take the homogeneous one, I mean,
exactly,
the homogeneous one. Okay, you want something that is not spatial homogeneous. That's nice. Maybe this is another. This could be another direction of investigation. Yeah, because I mean, your setting looks like nicely suited to that type of question. No? Yeah. So yes, I agree. And I have another quick technical question. It's so in this again with this type of in your general setting, are you able to prove if you look at the zero range process, are you able to prove the 2 blocks estimate or? No. Indeed. So I had no time to face with to discuss the zero range, but in the zero range, homogenization helps you a lot. But then you have to prove the 1 and 2 blocks estimate. You have the tightness of the empirical measure. You have a lot of steps thanks to homogenization, but at the end you have to use some percolation type arguments. For example, I did it for the zero range on the supercritical percolation cluster to get the second block estimates. So it's not for free. While in the exclusion process, in some sense, with homogenization, you close the circle. Yeah. Okay. Yeah. Thank you. Okay. Thanks to everybody. Thanks to everybody.
All right. Well, maybe we should stop now. So thank you for your talk, and thank you everyone for coming. And we'll see you next week. Okay. Thanks a lot. Bye bye. Have a nice evening or day. You too. Bye. Okay.